In this video, we will be solving 2021 C3. The problem goes, we have a circle and 2021 thimbles arranged around the circle. And the Thimblerigger performs a sequence of 2021 moves. In the kth move, he swaps the position of the two thimbles adjacent to K. So if we get a zoom in, and let's say this is K, and the two adjacent ones are A and B. So the Thimblerigger on the kth move swaps the position of these two thimbles right here. And we want to show that at some point in the kth move, the swapping happens so that K is in between A and B, value-wise. So A is less than K less than B. Or B is less than K less than A also works because we can just swap them. Okay, so this is the setting of the problem, and we want to see how we can actually work on proving this. The first thing we should notice is that 2021 is probably an arbitrary number because the year is 2021. So what we can do is we can start with some small cases and see if we can gain some intuition from them. So let's start with n equals 3. In this case, let me just throw in an arbitrary order. Let's say 1, 2, 3. So on the first move, we swap 1. So it becomes 1, 3, 2, and then we swap 2, so it becomes 3, 2, 1, and then we swap 3, so it becomes 3, 2, 1. Okay, and so if we look at this second move right here, 2 swaps 1 and 3, but 2 is between 1 and 3, so yep, that works. But if we think about any random configuration for n equals 3, it should always work because 2 will always be adjacent to 1 and 3. So that case is not very interesting. Let us try some other case. Let's say n equals 4. And this time, I'm going to throw in a construction looking like this. Let's try and see what will happen with this construction. So if I swap 1, then this becomes 1, 2, 4, 3, and now we swap 2, but 2 is adjacent to 1 and 3, so this will immediately work. But what we should do is we should try to probably construct something that hopefully doesn't work. So let's try a bit more. So we kind of want 1 to not be adjacent to 2, so that 2 can't do whatever it does in all these cases. So what if we place them opposite each other, and then we just place 3 and 4 on the other diagonal? Then we should get that 1 will swap 3 and 4, so it becomes 1, 3, 4, 2. Now 2 swaps, but 2 is adjacent to 4 and 3, and so there's not that problem anymore, and we get 1, 4, 3, 2. And then if we swap 3, we should get 1, or rather 2, 3, 1, 4. Finally, if we swap 4, we would get 1, 4, 2, 3. So if we notice in this entire process, it seems that, yes, there never happens to be a case when A is between, or A is less than K less than B. So is the problem statement wrong? Well, no. If we look more closely and analyze some more cases, it turns out that when n is even, there is a problem, but when n is odd, the problem statement always holds. So for example, if n was even, what we can do is we can label these positions as odd and even, and then we just place all the small numbers on odd, place all the big numbers on even, and it turns out that that will be a construction that does indeed work. So this so we found out that when n is even, this thing doesn't work. And the reason we did this is this helps us gain more intuition. So we now know that in order to prove this, we need to eventually somehow make use of the parity condition, because 2021 is odd. We need to make use of that condition right there. So let me just leave that there. Okay, so now we need to think a bit more, and eventually we should come across the notion of alive and dead, which is what I'd like to call it. So basically, let's say that it's after the kth move, so we just moved the kth move. If we look at the things, the thimbles 1, 2, 3, all the way to K, they've already done their move and they can't move anymore, so they're kind of useless. So let's call these dead. And let's call the other ones, which is k plus 1, k plus 2, all the way to n, let's call these alive. Call these indices alive. So this is during the kth move. And now what we can do is we can kind of scan a map of this configuration. So let me use this drawing right here. We're going to scan a map of this, and we're not going to focus on the specific indices. We're only going to focus on the dead and the alive. So very quickly, the reason we're doing this is that the entire situation is actually very dynamic. If you try to play around more with it, for example, if you say this thimble is going to swap these two, but then maybe before that, some other thimble is going to come in and swap this one away. And so things keep moving, and it's basically impossible to keep track of everything all at once. So with these kinds of settings, what we have to do in these combinatorics problems is we want to somehow find an invariant or coloring or just something that only keeps track of a certain part of all the information, which is related and hinted by the operations. Hopefully that will give us the information that we need to prove our contradiction, because it still encodes all the information. So that was a mouthful, but if we take a look at what's going on over here, in the beginning all of the thimbles are alive, or everything is alive. And so after each move, let's say we move this person. And by the way, in order to prove this, the strategy we're going to adopt is we will say that assume for the sake of contradiction that for each move, for each kth move, either both A and B are greater than K, or both A and B are less than K. So this is the exact opposite of what we're trying to do. So we assume this, and we will hopefully derive a contradiction which proves our claim. Okay, so if we look at this, initially they're all alive, and each time, let's say it's the first move and this is 1, then I will swap these two and I'll kill one, so one becomes dead. And so these two swap, but notice that these two are either both greater than K, let's call this K, or they're both less than K, which means that they're either both alive or both dead. So if we just look at this map right now, every time we perform an operation, we make an alive index dead, and we swap two indexes which are either both alive or both dead. And if we don't focus on the indices or anything, and we only look at the positions, you'll notice that the map shouldn't really change much. The only change should be this position going from alive to dead. So each time, exactly one position goes from alive to dead, and everything else stays the same because these things don't change, and these two have the same aliveness or deadness, and so they also don't change under the heat map. And so why is this useful? The reason is that if we have assumed for the sake of contradiction that there exists such a configuration, and we keep swapping, eventually that there isn't this thing, so each time A, B are either both greater than K or both less than K, then the heat map will have to change exactly like this. I don't know why I call it heat map, it is just interesting. But anyways, each time exactly one of the things transform from alive to dead. And there's also a condition for this thing transforming. Its two neighbors must either be both alive or both dead. And so now, if there exists such a configuration, then it is a necessary condition that it will correspond to one of these steps or chain of steps that turn our entire thing from alive. I'm going to denote alive by color. You know what? I'm going to denote alive by square. So there exists a chain of operations that turns our alive thing all the way into a completely dead thing. And naturally, we feel that this probably wouldn't be possible. And also we have to make use of the parity, because if it's even, our intuition tells us that this should be possible, and if it's odd, it probably shouldn't be possible. So one thing we can definitely do is we can just analyze how the thing changes. For example, we can, without loss of generality, say that this thing will turn into dead, alive, alive, and then this thing can't change until the other thing changes, so we need to change this thing. But yeah, that's just all very messy. And you know, even if you came up with a solution like that, it's not really elegant. So what we can do is we can take a look at some invariants again. So this is especially helpful because we're dealing with parities stuff, and we have these operations, and invariants are almost always very, very helpful here. So let's analyze the two operations we can have. There are only two. So we can have this. If we have 3 alive cells, we can make the middle cell dead and the other 2 alive. If we have 2 dead cells and an alive cell, we can change this into 3 dead cells. So what I'm going to analyze here is I'm going to analyze the relative relationships between each adjacent pair of cells. So with invariants, it's all about keeping track of some certain quantity. And for example, if we're just, the most obvious one would be the number of dead and alive cells, but that doesn't really give us much information here. Instead, we're going to analyze these relationships. So there are 3 types of relationships. They can either be both alive, I'm going to just call it square, square. They can be both dead, or they can be 1 alive and 1 dead. So here, I'm going to denote this by A, denote this by B, and denote this by C. So if we look at this relationship, this is an A, this is an A, this is a C, and this is a C. This is a C, this is a C, and this is a B, and this is a B. So again, we were talking about parity, so it's very natural to look at this and consider the parities. For example, there are exactly 2 A's, 0 B's, and 0 C's over here. Here, there are 0 A's, 0 B's, and 2 C's. So 2 goes to 0, 0 goes to 0, and 0 goes to 2. So the parity actually never changes. Similarly here, we should have 2 C's, everything else is 0, 2 B's, everything else is 0, and so the parity never changes. Which means that after we go through all these operations, the parity of the number of each of these relationships should not change. And so after we find this invariant, all we have to do now is to look at the beginning state and the end state and look at these quantities. For example, in the beginning state, there should be all alive, and there should be n of them. So there's n connections, and we're going to write n is equal to 2s plus 1 because n is odd. So there's 2s plus 1 A relationships. There are 0 B relationships and 0 C relationships. In the end, we should have all dead. So similarly, we should have 0 A relationships, 0 B relationships, or rather 0 A relationships, 2s plus 1 B relationships, and 0 C relationships. So if we look at this, 2s plus 1 changes to 0, and 0 changes to 2s plus 1. But 2s plus 1 is odd, this is odd, but zeros are even. So the parity does change, which is a contradiction because we have observed that it is an invariant. The parity never changes. So we arrive at a contradiction, which means that this cannot happen. We cannot have some map changing like this, which goes back, because this is a necessary condition, it goes back and tells us that we cannot have such a configuration. Okay, so we have proved the problem. And the main takeaway in this problem Well, first of all, the key insight to solving this problem is to notice the alive and dead map. I'm going to write that down here, alive/dead map. And I'm going to erase some of this stuff. But the key step is to notice this alive/dead map, because it can help us keep track of some of our invariants in our operation. For example, these are either both alive or both dead, so we were able to make use of that condition fully, which is why this thing actually worked. But the bigger question is, how do we come up with something like this? And to be honest, when I was solving this problem, I was just messing around trying to make sense of the setting, and I just thought about how if a cell is used, so let's say the index, the number of turn, which is the kth turn, it already goes past the index, then this cell is kind of useless and we don't need it anymore, so I'm just going to call it dead. So honestly, it's mostly just about playing around and getting an intuitive feel for everything, and eventually you should be able to come up with something like this. But then the other side to it is some combinatorics theory. Well, it's not really theory, but it's more about some tactics. So for example, the tactics here is, first of all, coloring. So I called it an alive/dead map, but essentially it's just a coloring. You color some cells alive and color some cells dead. And if we already know about this coloring tactics, then it's easier to spot this alive/dead map in this problem, which is again demonstrating how knowing these tactics beforehand can greatly assist your problem solving. And the other insight in this problem is to consider invariants. And if you do enough combinatorics problems and you know these tactics about invariants, it should come quite naturally. For example, when considering parity, invariance is one of your go-to options. So definitely we want to do more combinatorics problems and try to stack up on all of these tactics to hopefully apply them the next time you see a problem and hopefully use it to actually solve the problem.